Hello, in this video we're going to work on states of matter, which is chapter 13 in your textbook. So the big idea is intermolecular forces, also known as IMF for short, affect the properties of all states of matter. Now we're going to be talking about the states of matter such as solid, liquid, and gases for these lessons. So what does the word kinetic mean? So if we think back to maybe some physical science that we did in middle school, if we're talking about kinetic energy and we're talking about this new thing known as kinetic molecular theory, or also shortened for KMT, the word kinetic means motion. So when we think of kinetic molecular theory and the states of matter, we really need to talk about how they move. All matter consists of tiny particles that are in constant motion, even solids, as we're going to find out in each of our lessons. So we're going to focus on each state of matter. So there'll be a video for solids, liquids, and gases, and then we'll combine them all together for a phase diagram. So throughout all these lessons, whether we're talking about solids, liquids, or gases, we're going to represent them as circles or spheres if we're talking in the 3D model. So whenever I'm drawing diagrams, we're going to represent it as our circles for it. Now, if you're doing the digital notes, you'll see that you can draw along with me as we're going through it. So in this video, we're going to focus primarily just on solids. So let's look at some properties of solids first. Solids reflect an orderly arrangement of their fixed particles in these fixed different locations. So if we take a look at our diagram over here, we can see that they're fixed, but notice that they are vibrating, and we'll talk about the motion in the next slide. So most solids are tightly packed, which gives them that definite shape and definite volume. So if you're drawing along, we're going to draw them in an orderly pattern for it. Now, that's not saying that all solids are orderly. We'll look at some unorderly or disorganized different types of solids in this video as we're going through. So you can draw your circles, you can drag them in your notes right now. So are solids moving? Yes, they are. Under the kinetic molecular theory, we'll see that our solids are moving. Very slightly, the solids are vibrating in their fixed points, and we'll see that solids do not flow as per this. So if we're reviewing our solids properties, we'll see that they have the strongest IMF. So what's meant by IMF? It's that intermolecular force of our big idea. It's just the forces that hold them together. So if it has the strongest forces there, we'll see that they're going to be together, closer together, feeling that attraction from the other particles, like our bonding, such as ionic and covalent bonding. We'll see they have definite shape and volume. We can see this in our diagram there. We could see that it kind of has the shape of a cube, and if we had to take the volume of the cube, we could do the length times width times height. And we'll see that in that diagram of the last one, if I scoot back to it, we'll see that they're slightly vibrating in place. You wouldn't be able to spot it with the naked eye for it. So those are our basics of our solid properties for it. Now, most solid substances are crystalline, and a lot of times we even refer to it as a crystal lattice. So we'll see that our particles are arranged in an orderly, repeating 3D pattern, and that's what we refer to as the lattice. The shape of the crystal actually reflects the arrangement of the particles that make up it. So there are many different crystal shapes for it. But they all have this thing known as a unit cell. A unit cell is just the smallest piece of those particles that retains its geometric shape. So if we look at a tiny piece of salt under a microscope, you can see that it has that cubic shape for it. And if we look at a bigger crystal, we would see that that's its unit cell, and then it keeps making more and more of those cubes for that shape for NaCl. Notice that the red represents our Nas and the green represents our Cls. Now, which one would be the crystal out of these two? We have A right here, and we have B. So remember, a crystal is a repeating 3D pattern. So which one's repeating, A or B? Hopefully you chose A. So we can see that we orderly have these bigger pieces going in our rows, and then in between we have these smaller red ions for it. We would see that B looks very disordered there. Now, some solid substances actually have the ability to exist in one or more form, and that's what we're going to focus on now. It's actually known as an allotrope. Now, an allotrope is made of the same element but different in structure and properties, and carbon actually has three known allotropes. We can see it as the graphite of our pencils. Now, notice that it actually has kind of a honeycomb shape to it, and what we'll see with this honeycomb shape of it, we'll actually see that when you're writing, you actually shave off the top of that graphite, and then that goes onto your paper. Now, we'll see the diamonds made from a tremendous amount of pressure. You'll notice that the structure differs. It's still made out of carbon, but it's a much stronger substance. You'll even see on some tools that they have diamond tip on the tool to cut through stuff. Now, our last one is our Buckminster fullerene, which is actually a group of 60 carbons. And a lot of times we call it a buckyball because it kind of looks like a soccer ball. Now, I can't say Bucky without now thinking of the Winter Soldier. So if you're keeping up with Marvel, maybe you're thinking the same thing. Sometimes they even just call it a fullerene, meaning that it has our carbon 60 for it. Now, these are all allotropes because they're only made out of carbon. So we couldn't technically say coal because coal actually has other stuff in it besides just carbon. Now, what if a solid is not crystalline in its structure? Well, we call these solids amorphous. So as you can see in this unit, there's a lot of new vocab terms. We're going to see that an amorphous solid lacks an ordered internal structure. So whereas our crystal has a 3D repeating pattern, we're going to see an amorphous has a randomly arranged. They do not melt at a definite temperature like our crystals, and if we shatter them, they actually have irregular angles, jagged edges, unlike a crystal solid for it. So if we take a look here, we have our amorphous versus our crystalline. So we would see that the amorphous is not regular and aligned like our crystal structure right here. Yes, they're both solids, but this one lacks that ordered structure. Some examples include glass, rubber, plastic, anything that you really melt into pliable shape. Like if you're making a glass sculpture, you can melt it and then bend it to put it in it. The same thing with rubber and plastic for it. So at this time in class, we are done our solids. So we're just looking back at these properties to ask if we have any questions for it. And we had a bunch of new vocab terms for these solids. So thanks for watching.